In this lesson, I'm going to try to give you an appreciation for why logarithms are so important by talking to you about logarithmic scales. Now, before I talk to you about logarithmic scales, I'll give you a quick reminder about how logarithms work in the first place. So, for my reminder, I've written the log base 2 of 32 and the log base 10 of 100. We want to figure out what these two numbers are actually equal to. So a logarithm asks how many times we need to divide the top number by the bottom number to get to 1. So for example, in the case of the log base 2 of 32, we're actually able to divide 32 by 2 5 times. If we do it once, we get to 16, then we get to 8, then we get to 4, then we get to 2, then we get to 1. And that's 1, 2, 3, 4, 5 divisions. Alternatively, you can also think of this as the number of times I need to multiply this 2 by the number 1 to get to the number 32. So if you started with the number 1, you can multiply 1, 2, 3, 4, 5 times, and that will give you the number 32. So similarly, the log base 10 of 100 is just going to be the number 2, because you can divide 100 by 10 2 times, because 100 divided by 10 is going to be 10, and then divided by 10 again gives you the number 1. So that's 1, 2 divisions. So I hope you can agree that as far as concepts go, logarithms are not really that complicated, but their usefulness cannot be understated. So throughout the remainder of this lesson, I want to show you why they're so useful. So I've started off with a random number here, 6,783. Now most of the preceding discussion is going to center around powers of 10. So I want to write the surrounding powers of 10 to 6,783. So the number 6,783 is going to be bigger than 1,000, but it's also smaller than 10,000. Initially, this doesn't really seem so important, but it is going to be important if we think about the log base 10 of 6,783. So to show you this, I'm going to take the log base 10 of all three of these numbers. Now this leads us to the first interesting point here. If we know that these three numbers start off in order, then taking the log base of anything is always going to leave them in order. So to be clear, 1,000 is smaller than 6,783, and therefore the log base 10 of 1,000 will also be smaller than the log base 10 of 6,783. But then this actually allows us to quickly think about what the value of the log base 10 of 6,783 actually is. Because if you think about it, the log base 10 of 1,000 can easily be found. It's really just asking you, how many times can I divide 1,000 by the number 10 to get the number 1? Well, if you divide once, you'll get 100. If you do it twice, you'll get 10. And if you do it one more time, you'll just get the number 1. So you can divide it 1, 2, 3 times. So that just means that the log base 10 of 1,000 is just equal to the number 3. And I want you to notice that that's just the number of zeros that we have. If we apply the exact same logic to the log base 10 of 10,000, then we can divide 10,000 by 10 a total of 4 times to get to the number 1. So that means the log 10 of 10,000 is just the number 4. So this gives us some interesting insights into what the log base 10 of a number actually does. If we take the log base 10 of 6,783, it's between 3 and 4. And since this is a 4-digit number, the log base 10 is really just telling us how many digits our number is. So before I address that point further, I just want to say something else quickly. I'm saying that if numbers are ordered, their logs must also be ordered. So if we know that A is guaranteed to be less than B, then the log base C of A will also be less than the log base C of B, where C can be any number you like. So if this is always going to be the case, then I'll go ahead and address the point that I just made a minute ago. If you look at the number 6,783, if we were to just take the log base 10 of that and then round it down, we'd end up with a number 3. If you then just add 1 to it, you'd end up with a number 4. And you can see that this is a 4-digit number. And this is actually a really good way to find the number of digits in a number. So for example, if you started with the number 1,000 and then you took its log base 10, you'd get the number 3. 3 is already a whole number, so if you round it down, you still have 3. And then you add 1 to get to 4, and of course 1,000 is a 4-digit number. So to say this one more time, the log base 10 can help us find the number of digits that a number actually has. So we're saying that the number of digits in a number x is going to be the log base 10 of that number, and then this symbol over here tells us to round down. It's called the floor symbol. And then we just add 1. So to give an example here, we want to find the dig of 12789. So if we take the log base 10 of 12789, we can see that that's going to be bigger than 10,000, but smaller than 100,000. We know that the log base 10 of 10,000 is just going to be 4, as we found before. So if we rounded this down, it would just be 4. And now, 4 plus 1 is just equal to the number 5. So the dig of 12789 is just equal to 5. But as you can see, 12789 is a 5-digit number. So this correctly told us the number of digits in our number. Now, throughout this whole discussion, I didn't actually need to find the value of the log 10 12789 or the log 10 of 6783. It's going to be a number between 3 and 4, but we didn't talk about which number that actually is. So to explain this further, I've just gone ahead and picked another random number to illustrate this point. We can see that 12789 is smaller than 15938. And therefore I'm saying that the log base 10 of 12789 must be smaller than the log base 10 of 15938. Now this is something I'd like to actually demonstrate by typing both numbers into a calculator. So just remember that if we just type log without writing a base, it usually means the log base 10, especially in most calculators. But we can see that the log base 10 of 12789 is 4.1068, and the log base 10 of 15938 is 4.2024. So this should demonstrate that larger numbers always have larger logs, and that's actually pretty important if you're actually going to use logs to compare two different numbers. So one of the primary uses of logs is to compare numbers across multiple magnitudes. You can see that both of these numbers start with the number 4, because remember, if you round this number down and then you add 1 to it, it's going to give you the number of digits. So it makes sense that since they're both 5-digit numbers, both of these start with the number 4. So this idea, where you can turn a really huge number into a really small number like the number 4, while still preserving the order, is the main reason why logs are so useful. It allows us to compare numbers that are hugely different in size. So this is the main idea of a logarithmic scale. Because logarithms reduce the size of a number and keep numbers in order, then they are super useful to compare values that have wildly different sizes. So to show you this, let me start by actually drawing on an axis that has a linear scale like you're currently used to. So you've probably seen lots of scales like this one before. Scales that start at the number 0 and then increase by 1 as you move to the right, or really by any number that you like. So the way that these scales work is that every time you go up by 1 unit on the axis, you're going to increase the value by some fixed amount. In this case, I'm increasing the axis by 1 every time I go across. But of course, you don't need to increase it by 1. You could increase it by 20 or 50 or really any number you wanted to. If we wanted to turn this linear scale into a logarithmic scale, I want you to imagine that these markings are not really the actual numbers we're after, but the log base 10 of the number that we're after. Usually, we don't care about what the log base 10 of a number actually is. We want to know what the original number is. So for example, let's think about which number you would have needed to take the log base 10 of to get the number 1. Well, we already know that the log base 10 of 10 is going to be 1, because after all, you'd only divide 10 one time to get the number 1. We also know that the log base of anything where 1 is the input is always going to give you the value of 0. So the log base 10 of 1 must also be the number 0. And then we can continue filling out the rest of the values. We know that the log base 10 of 100 is going to be the same thing as 2, and the log base 10 of 1000 is going to be 3. So as you can see, on the top scale, every time we move to the right, we add the number 1. But on the bottom scale, it looks like we're multiplying by the number 10. And that means that the number over here is going to be 0.1. So if this scale on the top is going to be known as a linear scale, then this scale on the bottom is going to be what we call a logarithmic scale. It has a few interesting features here. First off, I want you to notice that the number 0 does not occur on the logarithmic scale. And in fact, it's never actually going to occur. And it makes sense that it never appears, because you'd be asking, how many times do I divide the number 0 by 10 to get the number 1? Of course, you can divide 0 as many times as you want, and you'd never get 1. The other interesting feature is that every time you seem to go to the right by 1, you seem to increase the number of digits in your number by 1. So all of these numbers over here are the 3-digit numbers, and all of these numbers are the 1-digit numbers. This also tells you something interesting about this dig function over here. If you applied it to a number like 0.1, you'd actually get 0. And that also makes sense because technically the first significant digit is going to occur at the 0th place. So really, the dig function is actually measuring the number of times you'd have to move the decimal point to the left so that it's just before your first significant digit. So for example, in this number, it's just 4. So at this stage, we have all the numbers that seem to start with 1, but you'd be right to ask, where does the number 20 actually go? Well, to show you that, let's take the log base 10 of 20. So we notice that the log base 10 of 20 is approximately equal to 1.30. And that means we should put it approximately at 1.3 on the original scale. So if 20 is going to go all the way over here, then we don't really have much space left for 30 up to 90. So let's figure out where 30 actually goes. So as you can see, the log base 10 of 30 is approximately 1.47, and that's almost halfway between the numbers 1 and 2. So this immediately indicates that the numbers are really going to be bunching up towards the right. Now, before I reveal the positions of all the rest of the numbers to you, I'm just going to do one more number, just for good measure. I want to compare the value of the log base 10 of 20 to the log base 10 of the number 200. So as you can see, the log base 10 of 200 is 2.30, and it looks like that's exactly 1 larger than what we had at the log base 10 of 20. And this is actually a general property of the log base 10. If you increase the value by a factor of 10, then you're going to expect the log of that value to increase by exactly 1 unit. And that immediately tells us that the log base 10 of 2000 would just be 3.30, and then the log base 10 of 20,000 would just be 4.30, and so on. So now at this point, I think you get the general gist of things, so I'm going to move away the calculator and fill out all the rest of these markings. So you can see that this is 10, this is 20, this is 30, 40, this is 50, 60, 70, 80, and 90. As you can see, the numbers really do bunch up as you get closer and closer to the next power of 10. And this is actually pretty cool, because if this is 1.47, then this value would be 2.47, and this would be 0.47, and so on. So this shows us that a logarithmic scale is a completely different alternative to a linear scale like this one. Depending on your application, sometimes a linear scale will make more sense, and sometimes a logarithmic scale will make more sense. But this is definitely best explained with an example. So let me go ahead and bring up an example, and we'll work through it together. So for this problem, I'd like to show the radius of each of these spheres on both a linear and a logarithmic scale. Now, not all of these are perfect spheres, but they're close enough. So in my list, I have a soccer ball, a famous tourist attraction somewhere in America, a meteor known as the Vespa meteor, the planet Earth, the planet Jupiter, and the Sun. So I've given you the approximate radius of each of these spheres. The soccer ball is 0.2 meters, the tourist attraction is 25 meters, the Vesta asteroid is 350,000 meters, the Earth is 6,371 kilometers, and then Jupiter is 69,911 kilometers. And then you've got the Sun, which is 696,000 kilometers. So let's start by just drawing each of these on a linear scale first. So I've had to actually mark this axis with 500 m. You can think of m as million, because we're going to need it to be at least large enough to put the Sun somewhere. The Sun is 600 million meters, as you can see here. So the Sun's going to go roughly over here somewhere. So if the Sun goes here, then we've got to think about roughly where Jupiter goes. Now Jupiter is going to go very, very close to here, because 69 million is a lot smaller than 696 million. So it's going to be 10 times closer to the 0 line. But then if Jupiter's showing up over here, then where are these four showing up? Well, they're going to be so close to 0 that you're not even going to be able to tell that they're not at 0. So this scale is actually totally useless for comparing these different values. So as you can see, all of these spheres just bunch in very, very close to 0, and the only one that really shows up is the sun. So we can actually fix this by redrawing this on a logarithmic scale. So I've tried to draw the same logarithmic scale that I talked about before. As you can see, the log base 10 of the number 1 is going to be 0, the log base 10 of 10 is 1, and then the log base 10 of 100 is 2, and so on. We also see that the log base 10 of 0.1 is minus 1, and 0.01 is minus 2. And to keep the numbers in check, rather than writing heaps of zeros, I've written k for 1,000 and m for 1,000,000. So this is 1,000, this is 10,000, and this is 100,000. This is 1,000,000, this is 10 million, and this is 100 million. And this number over here is a billion. So now, let's just graph all of the spheres the same way we did before. This number over here is 600 million, and that's going to show up roughly between 100 million and 1 billion. So that's going to show up roughly over here. If you're interested in exactly where it goes, of course you could just type in the log base 10 of this number into a calculator. So the log base 10 of 696 million is approximately 8.84, so it shows up right here, as we saw. Now for the rest of the spheres, I'm not actually going to type the log base 10 into a calculator. You should check them yourself to make sure everything I'm doing makes sense. So after this, we need to place Jupiter, and Jupiter is going to be somewhere between 10 million and 100 million, so it's going to show up roughly over here. And then after this, we want to place the planet Earth, and that's going to be somewhere between 1 million and 10 million, so it's going to go roughly over here. Now the Vesta asteroid is 500,000, so that's somewhere between 100,000 and 1 million, so it's going to show up right over here as well. Now for the tourist attraction over here, it's going to be somewhere between 10 and 100, so it's going to show up over here. And finally, we have the soccer ball. So the soccer ball is going to be somewhere between 0.1 and 1, so it's going to show up right over here. So as you can see here, we've presented the exact same information here and here. I should technically make this R, so let me do that. But despite the same information being on these scales, I think you can agree that this scale on the bottom is way easier to read. Now the main reason this is easier to read than this in this particular example is because this data spans many orders of magnitude. This is really, really small, and this is really, really large. In case you don't know what an order of magnitude is, it's just the multiplication by 10. So this is one order of magnitude, and then increasing by 1 takes you to the next order of magnitude. So anytime you have data that spans many orders of magnitude, a logarithmic scale is probably more appropriate. But if you have linear data, you should probably use a linear scale. But that just about completes the example I wanted to show you. So let's go ahead and summarize the lesson. In this lesson, we talked about logarithmic scales. And we said that logarithms have a few special properties that allow us to construct logarithmic scales like this one. For starters, we said that if you have some number like 6783, it's going to be between 1000 and 10,000, and therefore its logarithm is going to be between 3 and 4. Or, more generally, if we know that some number a is smaller than another number b, then the logarithm of a is always going to be smaller than the logarithm of b. Now the thing that makes the log base 10 so special is that it can be used to approximately tell us how many digits there are in a number. If we take the log base 10 of a number and then round it down and add 1, we will get the number of digits in that number. Or, to be more precise, this dig function actually tells us where the first significant digit appears. So, because logarithms reduce the size of a number, and they keep numbers in order, that made it possible to compare different values that have wildly different scales. So these two properties allowed us to actually build this logarithmic scale that we showed down here. To build a logarithmic scale, we just start off with some number and then take the log base 10 of it. The log base 10 becomes where we actually place that number. Now, logarithmic scales have a few drawbacks. For example, they can't show the number 0 or any negative numbers. But as we showed in the example, they are very useful to compare different numbers that have wildly different sizes. As you study more science and more maths, you'll meet many different quantities that are much better represented on a logarithmic scale rather than on a linear scale. So therefore, Being able to fluently read a logarithmic scale like this one over here is actually a very handy skill to learn, because it will be something you likely have to use many times in the future. But at this point, I think that just about completes everything I wanted to say about logarithmic scales. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.